Okay, we take a look at question 4. Question 4 goes calculate the quality of heat, that's the quantity of heat required to completely convert 20 grams of ice at 0 degrees Celsius to water at the same temperature, given specific latent heat of friction of ice as 33.6 joule per gram. So the information we have is that to calculate the quality of heat of quantity of heat required to completely convert 20 gram of ice at 0 degrees Celsius completely to water. So we are trying to convert ice to water at this temperature, and this is the quantity of the ice given. Then, and the specific latent heat of fusion of ice, the specific latent heat of fusion of ice is given as 336 joule per gram. So how do we go about this? Um, Ice is the solid form of water. So in converting it completely to water, that means we are trying to melt it. That is a melting process. Melting process. So it involves change of phase from solid to liquid, and if it is also called fusion. This is also called fusion. As we know, conversion from liquids to solids is called freezing or solidification. The conversion from liquids to gas, that is vaporization. The conversion from gas to liquid, condensation. Solid to gas directly without being converted to liquid, that is sublimation. So this is a case of melting, that is friction. So we're converting ice at this temperature to water completely. That is 20 grams of ice. And we're given the specific latent heat of fusion of ice. So the specific latent heat of fusion of ice is actually the quantity of heat required to convert 1 kilogram of a unit kilogram, 1 kilogram of ice to water. That is that about the specific latent heat of fusion. The heat required to convert ice from to convert ice completely to water, that is 1 kilogram of ice. It's called a specific latent heat of fusion. So there are you have to know the difference between when you say latent heat, then there is this sensitive heat. Then we do have the specific heat, like we have heat capacity. Then we now have specific heat capacity. So latent heat of fusion, then we have specific latent heat of fusion. When specific precedes latent heat of heat capacity, then it means it requires a unit mass of the substance. So, for instance, heat capacity of a substance is the heat required to raise the temperature of that substance by 1 degree So the heat required to raise the temperature of the entire mass of the substance by 1 degree. But if you're interested in the heat required to raise the temperature of a unit mass, like 1 kilogram or 1 gram of the substance by 1 degree, then we now have to attach specific. So it means specific heat capacity. So that is different. Then latent heat and sensitive heat. Latent heat, the word latent means hidden. What is not felt, unfelt heat. Like if water boils, for instance, or during melting of ice, if you want to melt an ice, then you have to apply heat. You have to heat it. So if you heat it, then if you put a thermometer, you will notice an increase in the temperature as you are applying heat. But at a point where the solid, ice in this case, starts melting, then the temperature remains constant, even though you are still adding heat, but it does not reflect in change in the temperature. So the temperature remains the same, even though you are still adding heat. Then why is the heat going? So such a heat that is not felt is said to be latent. But sensitive heat is that heat that actually, you know, result in increase or decrease in the temperature as you apply the heat. Like the heat you apply to water. If you want to vaporize water, you want to turn water into vapor, entirely vapor, steam. You first have to heat it. When you're applying heat, you need both sensitive heat and latent heat to achieve vaporization of water. So you're going to heat it to 100 degrees Celsius. They say you have your water at 25 degrees Celsius and you want to vaporize it. So you have to heat to 100 degrees Celsius. So the heat you apply here is a sensitive heat. And that you can see from the thermometer. The heat rises, the temperature rises as you apply heat. But the moment the water is at 100 degrees and then you keep putting heat, so it begins to it attains the boiling point, the point from which it now starts changing into uh, the other phase, which is the vapor phase. So at that point, you are not going to notice the increase in temperature. The temperature is going to remain 100 degrees Celsius, even though you are still adding heat. So that heat you are adding that is not reflecting in changing the temperature is the latent heat. So if it is in evaporating water, you call it latent heat of evaporation. So so on and so forth. So here the formula we need to the question says we should do what? We should calculate the quantity of heat required to convert this. So that's the question, the quantity of heat to achieve this convection. So the equation is simple. The quantity of heat Q is the mass multiplied by the latent heat. So heat is measured in joule. So if it is a large unit, then you can express it in kilojoule, megajoule, and so on. If you want to actually check from this formula if this is the right formula for calculating the heat, the, we do dimensional consistency. We see how if the units, the product of the unit of mass and the latent heat will give us joule. Mass is given in gram, then multiply by latent heat is in joule per gram. So you can see gram cancels gram, giving you joule. So which means this actually represents an energy, a heat energy. So we go ahead to directly substitute, which will give 20 multiplied by 336. So let me get my calculator. Okay. Where are we? So if we go like this, we're going to have 6720, 6720 joule, which in kilojoule, if you divide by 1000 to convert to kilojoule, then you should have 6.72 kilojoule. So I hope that is understood. So the formula is as simple as that. Then in fourth round, so this okay. I think we'll move to the next question. If we come across a question under this topic, then we're going to see more about it. That's actually what I wanted to explain before, but I think when we get to a question that calls for that, then we are going to give further explanation. So the next question is an object of mass 10 kg requires 20. I hope the right question. No, no, no. This is not question four. So the question we solved, we actually jumped. I just found out it is not question number four from here. I think this is question 9 or 8, like that. Sorry. So actually, the question number four is different from that. Question number four is a car of mass 100 kg moves at a constant speed of 10-20 meters per second along a horizontal road. A car of mass 100 kg moves at a constant speed of 20 meters per second. It moves at a constant speed of 20 meters per second along horizontal road when the power development by engine is. So the power developed by engine is the question. I found out this question is not complete. The complete question after search is that a car of mass 100 kilogram moves at a constant speed of 20 meters per second along a horizontal road, while the friction force is 200 newton. So there is actually a friction force which is 200 newton, and then the question says calculate the power developed by the engine. So those who printed the questions made the mistakes in omitting some of the parameters given. So it happens in most of the questions in this paper I have. So the question is the power developed. Power developed by the engine. So a car moves along a horizontal road. The car has this mass. It moves along a horizontal road at a constant speed of 20 meters per second, with the frictional force being this, the power developed by the engine. So power is the question. Of course, if there is a friction on the road, to overcome this friction, some energy has to be expended. Then the rate of expending this energy is the power that we are asked to calculate. So which means some work is going to be done by the car to overcome this force. So if you're able to calculate the work, then we just go ahead by dividing it by the time to get power. Because power is actually the rate of doing work. It could be work over time. It is same as energy expended or the rate of expenditure of energy over time. So whichever one. So now, so how do we now go about this? And we know that if you are to use work over time, work is force times distance in the direction of the force divided by time. So if we know first from the question, distance not known, even time also is not known. So now let's see how we're going to go about it. So we're going to use the work over time formula. Like I said, work is force times distance. So in place of work, we're going to write force times distance, then over time. Then we can go further to say this is force multiplied by distance over time, so that we can now say distance over time is velocity or speed. So velocity is distance over time. So that is to say that we can actually calculate our power as what? Force multiplied by velocity. So which the force and the velocity of which we have in the question, the velocity is 20 meters per second, and the frictional force has to be overcome is 200 Newton. So this gives this by substitution, this should give us 200 multiplied by 20, which ordinarily should give us 4,000. If we should give us 4,000, so power is measured in watts. So we can say this is 4,000 watt, or what is called joule per second. Joule per second, but joule per second is the same thing as watt. So 4,000 watt or 4 kilowatts should be the answer. If you look at the option, we're having 200 watts, 300 watts, 400 watts, 500 watts. So it's actually 4,000. They made a lot of mistakes, except if maybe the first is 20 Newton instead of 200, or this is 20 meters per second. So whichever way. So the answer is supposed to be 4,000 watt. Okay, I hope this is understood. So the formula is simple. The formula for power is work over time. But because our work is first and distance, we don't have the distance, we don't have the time. But we can rearrange the formula such that distance over time is the velocity which we have, and then we substitute to get the answer. I think that is as simple as that. So the answer is in watts, which is equivalent to joule per second. Then we move to the next question. So the next question, says, according to Newton's second law of motion, According to Newton's second law of motion, according to Newton's second law of motion, A, momentum is proportional to force action. B, action is equal to reaction, but in the opposite direction. So this very B is not is the third law of third Newton's law of motion. It is the statement of the Newton's third law of motion. So it has nothing to do with the second law. C, impulse force is universally proportional to time. That the impulse force is proportional to time. That is also not correct. The force is proportional to rate of change of momentum, which is the correct option here. I think in one of our previous questions we treated, we saw what impulse is all about. We discussed the Newton's second law of motion. Now, the statement of the Newton's second law of motion is that force is directly proportional to the rate of change of momentum. And the rate of change of momentum is this. So from which we get Ft equals m into v minus u. So where we say this is the impulse, meaning impulse is Ft, then rate of change of momentum is what? M into v minus u. So if you now look at the options, you can see that Newton's second law expresses a force being directly proportional to the change of momentum. So the answer momentum is proportional to force action is wrong. Action is equal to reaction, but in the opposite direction is wrong. Impulse force is universally proportional to time. Impulse force is not directly proportional. It's actually inversely proportional to time, not directly proportional. If not, as our time should have been found here, not as inverse. So the answer is the force is proportional to the rate of change of momentum. Force is proportional to the rate of change of momentum. This is change of momentum over time, then it becomes the rate of change. I think that answers that. So the next question is about the quantity of heat needed to freeze 1 kilogram of meat at its freezing point is known as A, heat capacity, B, latent heat of fusion. So I think this will treat in the next video.